welcome to another lesson from Level Up Mathematics. In today's lesson, we will be looking at the transformations of quadratic functions, part 2. In our previous lesson, we were exploring vertical and horizontal shifts in quadratic functions and how they shifted the parent function up, down, right, and left. Today, we'll be looking at dilations of quadratic functions. Our first dilation is a vertical stretch or compression. Vertical stretches and compressions are another way to transform quadratic functions. When a function is vertically stretched or compressed, the y values of the original function are multiplied by a given value and can be represented by a times f of x, where a cannot equal 0. So let's do an example of this. In example 1, it says the parent function f of x equals x squared is shown on the right. So here, this dashed parabola is our parent function f of x. In part A, it says use technology to graph g of x equals 2x squared and sketch the graph to the right. And then it says for g of x, what is the value of a, and how does the graph of g of x compare to f of x? So in any graphing calculator, I'm going to use Desmos, but you could use any graphing utility. I'm going to put in our first function, which is 2x squared. So our vertex, let's see, on my calculator graphed it in red, so I'll graph it in red on our notes. The vertex in this problem stays at 0, 0. But now the y values are being stretched. So on our parent function, we had a point, we went up 1 and over 1 to our first point. When we stretched the y values by a factor of 2, now that the y value of 1 is going to be multiplied by 2, which means we're going to have, on our new function, we'll have a point at 1, 2. And then we need a point on the other side. So here, our graph becomes more narrow when we multiply, the y values. So it says for g of x, what is the value of a? So the value of a in this problem is equal to 2. And how does the graph compare? This would be a vertical stretch because the y values were stretched by a factor or BFO of 2. Vertical stretch by a factor of BFO of 2. All right. Now, using technology, graph h of x equals 1/2 x squared and sketch the graph to the right. For h of x, what is the value of a, and how does the graph of g of x compare? Well, that should say h of x. H of x compared to f of x. So here we're going to have 1 over 2, side arrow, x squared. So when we have f of x equals 1/2 x squared, let me change to a blue pen here. Now our y values will be compressed by a factor of 1/2. So instead of having a point at 1, 1, we're going to have a point at 1, 1/2. The y values are compressed by a factor of 1/2. So your graph is going to get, well, that is not a very good parabola, but you can see on Desmos what it looks like. So the value of a here was 1/2, and this is called a vertical compression by a factor of BFO 1/2. What it means is that every y value is going to be multiplied by 1/2. So in your original function, if you had a y value at 8, your new y value would be at 4. So let me just change this to other things. Let me just change this. If I could change this to say 1/4 x squared, you would even get wider. Let's see, what if I changed it to 1/8? You can just get wider and wider, but your y values are going to continually be compressed. All right. So let's set up a couple definitions here. To get a vertical stretch, it says if the absolute value of a is greater than 1, a times f of x will vertically stretch and the parabola will appear narrower. So some examples of this might be f of x equals 5x squared. So let me just show you some of these. Let's see, there's my parent function. Let's say I put in 5x squared. You can see that's very narrow. Another example might be f of x equals 5 over 2 x squared. 5 over 2 is equal to 2.5, and 2.5 is greater than 1. So let's see what that would look like. 5 over 2 side arrow x squared. Okay. You could have g of x is equal to 8.7 x squared. As long as that coefficient is bigger than 1, it's going to stretch. So 8.7 x squared. Okay? The bigger you get, the more those y values stretch. Now, let's look at something called compressions. When the absolute value of a is between 0 and 1. Now, think in your head, what kind of numbers are between 0 and 1? Okay? A times f of x will vertically compress, and the parabola will appear wider. So, for example, if I need a number that's bigger than 0 and smaller than 1. So say I had 0.2 x squared. All right, that gives me, so let me write down that example. G of x equals 0.2 x squared. 0.2 is bigger than 0 but smaller than 1, so it's wider than the parent function. If I had f of x equals 1/10 x squared. 1/10 is bigger than 0 but smaller than 1. Let's look at what that would look like. Fraction 1 over 10 side arrow x squared. So again, you can see that we have a vertical compression and the graph appears wider than the parent function. Now, let me show you how this has been tested in previous standardized test type questions. So in example 2, it says the quadratic function f of x equals x squared. So here's our original function, this dashed parabola. It's transformed to create g as shown in the graph. Which transformation rule could describe g? Now, the first thing I want you to do is look at this graph and say, did the function get wider or narrower? Okay, hopefully you said narrower. So if it's narrower, then a must be greater than 1. So a must be greater than 1. Okay, so I'm going to eliminate answer A and answer D because I know the value of A must be bigger than 1. Now, for B and C, we have two functions that both have an A value of 2. So those are both possible answers. So let's see how else this graph transformed. So here was our original function. Here is our new function. So this function went to the left 3 and down 2. So when your function moves left 3, remember we do the opposite of what's in the parentheses. So that would be plus 3. And then down 2 would be minus 2. So now we know we have to go with answer choice B. All right. Now we can also have a reflection in a quadratic function. Quadratic functions can be reflected across the x-axis by multiplying f of x by a negative number. So watch what happens to the parent function when I multiply it by a negative 1. So if I had, here's the parent function, x squared. What happens if I put in negative x squared? All it does is reflect it or folds it over the x-axis, all right? What if I had negative 5 or negative 10x squared? Let's do that. So it still opens downward, but it's going to be very narrow. What if I had negative 0.2 x squared? Negative 0.2 would make it wider, and the negative would make it open down. So anytime you have a negative, you're going to reflect across the x-axis. So in example 3, it says for each equation below, each equation below represents a transformation of f of x equals x squared. Give a verbal description for each transformation and then determine the vertex and make a rough sketch. So we have, in our first problem, we have a, g of x is equal to negative 5 times f of x. Well, because of the negative, we know it's going to reflect across the x-axis. And then the 5, when a is greater than 1, it's going to be a vertical stretch by a factor of 5. So that means it's going to be a narrow graph. So we're going to make a rough sketch here. It doesn't have to be anything fancy, but I want you to make a very narrow parabola which opens downward. So I'm just going to put my vertex is still at 0, 0, and then I'm going to make a narrow parabola here that opens downward. So that's a rough sketch of that transformation. All right. In problem B, it says g of x equals 1/5 times f of x minus 3. Now, because that function has been multiplied by 1/5, that's going to be a vertical compression by a factor of 1/5, which means it's going to be wider. And then the f of x minus 3. Because that minus 3 is inside the parentheses, that means it's going to move to the right 3. So the vertex here, if it moves to the right 3, will be 3, 0, and it's going to have a wide graph. Our vertex is going to be 3, 0, and it's going to have a wide graph. So again, this is going to be a very rough sketch. Nothing fancy. 1, 2, 3. You're just trying to visualize what it's going to look like. So I'm going to draw. That is a very terrible parabola. Let me try that one more time. I want to draw a wide U-shaped graph that has a vertex at 3, 0. All right, problem C. We have negative of f of x plus 2 plus 3. So the negative means we're going to reflect across the x-axis. Now, the f of x plus 2, because the x plus 2 is in parentheses, that means we'll go left 2. And then the 3 is on the outside of the parentheses, and it's positive, so we'll go up 3. So my new vertex is going to be left 2 would be -2, up 3 would be +3. So let's draw that in first. Go left 2, up 1, 2, 3, so maybe right here. Then you're going to reflect it across the x-axis, which means it opens down. So it's going to look something like that. Now, I think we forgot to list our vertex on the first one, so that was at 0, 0. All right, quadratic functions can also be stretched and compressed horizontally by multiplying the x values of the function. This transformation can be represented by the notation f of b times x. So notice now your coefficient is not in front of the function, it's inside the parentheses. And anytime you have something inside the parentheses, it only affects the x values. Now, if your absolute value of b is greater than 1, then f of x will horizontally compress. And the parabola, it will horizontally compress the parabola, making the parabola appear narrower. So, for an example of this, if your b value is greater than 1, let's say you had f of x equals parenthesis 4x parenthesis squared. Let me show you what that would look like. Parenthesis 4x parenthesis squared. You would get a very narrow, because what's happening here are your x values. We draw an arrow. They are compressing in. They're compressing in, okay, making the parabola appear narrow. So another example might be g of x equals 7 over 2. That's equivalent to 3.5, so that's still bigger than 1, x squared. So I'll show you what that one would look like. Parenthesis 7 over 2, side arrow, x, close parenthesis squared. So again, very narrow, all right? All right, now, if your b value is between 0 and 1, then f of b times x will horizontally, this time, your x values are stretching outward. So they will horizontally stretch the parabola, making the parabola appear wider. So examples of this, let's see, if you had f of x equals, I don't know, parenthesis 1 over 5 x squared. So 1 over 5 is bigger than 0 but smaller than 1. Let's look at what that would look like. First of all, let me put our parent function here. Here's our parent function. All right, let's talk about if we had parenthesis 1 over 5 x parenthesis squared. So your x values vertically stretch. The parabola would become wider. If you had something like this, f of x equals x over 7, that's the same thing as 1/7 x. So I'll show you how that you would type that in. Parenthesis x over 7, side arrow, parenthesis squared. Okay, your parabola will stretch horizontally and become wider. Now, here's an example of how this has been tested in the past. It says the graph of f of x equals x squared, and g of x equals parenthesis 3x parenthesis squared. What is the value of b, and how does g of x compare to f of x? So here's your original. It's the dashed. So notice, to get to the new, you have to horizontally compress or make it smaller, so to get the new graph. So the value of b in this problem is +3, and it's a horizontal compression Okay, let's see. And it appears narrower. All right, example 5. The graph of g of x equals x squared was transformed to create the graph of h of x equals x over 4 quantity squared, as shown in the graph below. Which of these describes the transformation from the graph of g to the graph of h? All right, because the x over 4 is inside the parenthesis, we know it's going to be a horizontal. Oh, goodness, excuse me, I marked out the wrong ones. Because, again, let me just say this again. Because our x over 4 is inside the parenthesis, we know we're going to have a horizontal dilation. So I want to get rid of the ones that say vertical. So it's got to be either a horizontal stretch or a horizontal compression. So the dashed parabola is your original. So notice to get to the new, we have to stretch out our parabola. We have to stretch out of our parabola. So this would be a horizontal stretch. And that concludes today's lesson, Transformation to Quadratic Functions, Part 2.